Right. So now we'll talk about supports and structures or structural supports. Structural supports. Okay, so structural supports, we also have to make idealizations of the supports, just like the structural members that we uh, make idealizations, models, structural models, so that we can actually do the analysis or computations for solving the sizes and stuff like that. So for the structural supports, we also have to make idealizations. Now recall that the structure is composed of many structural members that are connected in some way or another. So for example, a beam. So a beam, let's say a steel beam, rests on a girder, a much larger beam, and then the girder rests on, let's say, a column. So this connection or this joint actually must be idealized, and that's what we call as a structural support. So how do we model that? Okay, so we have two purpose of a support. Support or joint. Okay, so when we say support, usually that's the ends, and we say joint. Sometimes we use the I mean, it also includes the internal release or something like that. Okay, so join something like a connection of the two members or many members. Whereas for support, sometimes you just use it for the ends, or let's say the boundary conditions of the structural member. Okay, so the two purpose is that number one, the static function, one static function, and another purpose is to provide a kinematic function. So when we say static function, then from the word static, then it has to do with the forces, transmission of forces. Okay, transmission of forces from one member to another, from one to another. Whereas the kinematic function it's about the relative movement. Okay, relative movement between members. Or something related to the degrees of freedom. Degrees of freedom. Okay, so static functions it's about forces, whereas the kinematic is about movement. So if you recall in engineering dynamics, that's at least gives the idea of what it should be about. So this should be about the movement, the relative movement between the members. Okay, so we have three types of supports that's common, although various support models are enumerated in, let's say, static textbooks, and also includes three-dimensional structures. So for us here, we'll only consider uh, three types. So number one, we have pin connection, or we'll start off by okay, we'll start with the roller support. Then another one is the pin support. Then the third one would be the fixed support. Okay, so the roller support, we use the symbol like this, or in other texts just simply use the something like this, just a circle. Okay, to express that it's a roller. This one, the pin support, this is the typical symbol, and then for the fixed support, see, there's also another one. I think we should include it, the free end. Okay, it's not just 3, although this is the most common, but this is another type of support, free end. So it's just blank. We don't use any symbol here. Okay, so this type of structural supports can be understood if we try to look at the static function and the kinematic function. So meaning that we'll look at each support in terms of the transmission of forces or support reactions, and then the other one is the movement. Because of that force, then of course there's gonna be some movement. Okay, so for a roller support, this type of support would have only one in terms of forces. It has one support reactions. Okay, so meaning if it has a support reaction on this direction, then meaning that it cannot go along the vertical. So it cannot, so it's something like it is constrained along the vertical. It is only free to move along the horizontal, but also it is free to rotate. Like for example, a beam, then it can rotate. Okay, I guess before that, I'll try to discuss first the possible reactions and then the possible movements. Okay, so we have this reaction, and then the movements. Okay, so recall that in our 3D discussion, the 3D equilibrium model that we discussed during our engineering static course, that we have a three-dimensional, let's say a three-dimensional structure. So we have X, Y, and Z. So meaning that we can only have support reactions along X, Y, and Z, and also rotational force, which is the moments. So since we are only dealing with 2D structures, then meaning that this is these are the forces that can only be considered. So we have forces along X. So let's say we have forces along X. So that's Fx, or it's just a symbol. You can use other symbols, but the point here, there's a support reaction. There's a reaction along the X direction. Then there's a reaction along the Y direction, so Fy. Okay, and then there's also a in order to maintain the equilibrium, then there must be a reaction moment, a reaction rotational force, and that's what we call the moment along the z-axis. So mz. Okay, so meaning that our reaction would be reaction along X along Y, and rotational, so let's say force reaction. Okay, so we'll just write down force reaction, and then moment reaction along z-axis. Okay, so that's it. So force reaction along X, force reaction along Y, and then a moment reaction along Z. Okay, so that's the 2D. So in terms of movements, then we can also have displacement or movement along X, or translation, we can call that translation along X. then translation along y, and then rotation along z axis. Okay, so these 6 are the possible reactions and movements. Okay, so meaning that the supports that we discussed, the principle just lies in this three reactions and then 3 movements. Okay, so for a roller support, the assumption is that there is a reaction. Let's say this is x and y, for example. So let's say this is x and this is y. And then the z-axis is orthogonal to the page, meaning at 90 degrees to the page. So the reactions we have along the y. So let's write r, y. But it has no reaction along the x. So meaning that if there's a reaction, you can also think that it is preventing the movement. So if there is a reaction along y, then meaning it prevents movement along the y-axis. If there is no reaction along the x-axis, then meaning it is free to move along the x-axis. Okay, so note that this is the point of this is actually the point that we consider, because that's where that's the point where the structural member is connected to. Okay, so let's say we have a beam here. So we don't have a moment reaction, so meaning that this beam is free to rotate. Okay, so it's free to rotate. Okay, so for a pin support, we have a support reaction along y, and we also have a support reaction along x. So meaning that it doesn't allow movement along y, it doesn't allow movement along x, but the rotation of a member is allowed. So meaning that this member is free to rotate. So okay, for the fixed support, let's say this is the beam, then the fixed support model has 3 support reactions. Okay, so we have Rx, Ry, and a moment reaction. So take note that these are reaction forces. This is not an external force. This is not also internal force. Okay, so external force is the loading. So for example, this is the force. My hand is the force, and I'm trying to apply force on this ball pen. So because of this external force, then actually the member also develops reactions. Okay, so the support here develops reactions. So it's different. The support reactions are different. Okay, so the free end is basically since it's free, then meaning it is free to move along the x, y, and rotation. So that is why it's just like that. Okay, so now if we try to tabulate the reactions, so we can say x, y, and then the z. Okay, so say roller. So if it's a roller, then we have only reaction along y. But take note that that depends upon the problem. But the point here is it can be the reaction is along x. So let's say for the case of this type. Okay, so if that's the case, then the reaction is along x. Okay, so the point here is for rollers there is just one reactions, but for pin support, then we have 2 reactions. Then for fixed support, we have reactions here, and then a moment reaction along the z. Okay, so I hope this is clear. So now, where can we use this pin support or roller support or fixed support? Okay, so for fixed support, that's very typical. And as I have said, that depends upon the designer on what models will be used. Like for example, the trusses that I mentioned in the previous video, that the joints of the truss, we said that it's welded, right? It's welded, but then it is. I mean, in analysis, we just assume that it's a something like a pin support, and that's actually internal releases. Okay, so I think we'll discuss also the internal releases. Okay, so internal release is something like it's actually a joint, but it's more on the internal of the structure. I mean, not at the boundary or something like that. Because for example, we have this portal frames. So imagine we have this pin support. So the pin support, if you notice that we have how many unknown reactions do we have? So we have 1, 2, and then 1, 2. Of course, let's assume there's an external loading. So we have 4 unknowns, but internal releases. Let's say we put an internal hinge. Okay, so meaning instead of transmitting the, for example, we have loadings, we have external loadings. Okay, so instead of okay, let's erase this, of passing the moment, the internal moments, okay, the internal loads to the other members, then it actually releases it. So that's why it's called internal releases. So meaning at this point, if our internal release is a pin, then meaning that there is no moment. Okay, so moment release. Of course, if there's moment release, then there's gonna be, like for example, axial or shear. So, but the most common ones for the structures are this one, the moment release, or referred to as internal hinge. Okay, so that's it. So actually, the use of internal releases actually simplifies the structure. Later on, um, when we discuss the topic on determinacy of the structures, then we'll be able to notice that by adding the internal release, that makes our or it lessens the degree of determinacy or indeterminacy of the structure. Okay, so for example, we have four unknowns, and we only have 3 equations of equilibrium available. So meaning that we have indeterminacy to the first degree. Okay, so meaning we cannot solve the structure using equilibrium equations alone. Okay, so but if we are adding this internal release or moment release in the structure, that actually adds another equation at this point. So meaning that this decreases the number of unknowns. So instead of 4 unknowns, then that's going to be 3 unknowns left. Okay, so we'll discuss this later. Okay, so we'll continue now the applications of these structural supports. So as I've said, the trusses, it's actually fixed support, but you can we analyze it as a pin support or internal hinge. Okay, so fixed supports is actually common. It's actually common to use in sample reinforced concrete columns and the joints between the reinforced concrete beam and reinforced concrete columns. So since they are casted, actually it's not that it's casted um, in one casting, but rather probably some cold joint here or something. Okay, but the point here is that makes a rigid joint. Okay, so meaning rigid joint, fixed meaning you can consider moments, the forces along x and along y. Okay, another one is the base plate. So the base plate of a steel column, for example. So this is the base plate, and then it rests on a pedestal. So the base plate has let's say four bolts, four anchor bolts. Of course, so if you have that four bolts, then meaning that you cannot, this base plate does not allow you to move along, let's say X, Y, and Z. So that's, for example, our X, Y, Z. So it doesn't allow movement along X, Y, or rotation along the Z axis. Okay, so that's gonna be a fixed support. Okay, so for pin support, another good illustration, by the way, with regard to this support reaction is the one given in the textbook of I think that's the Mechanics of Materials by Timothy Philpott. So it's a beam column connection. Okay, so for example, this is our steel column, and then this is the flange of the beam. Okay, so the terminology is that this is the flange of the beam, and then this is the web. If there is a extra plates welded on top, restraining the if it restrains this top flange and then the bottom flange as well as the web, let's say extra plates welded to the column and then welded to the beam, then meaning it's actually making a rigid joint. It doesn't allow movements along X, Y, and rotation along Z. So meaning that we can analyze this as, or we can idealize it as a fixed support. But if the connection is, for example, only along the web, okay, so let's say we have a bolt here or something that's only on the web. Okay, so that's the bolt. This type of connection can be idealized as a pin connection. Okay. Why? Because it allows actually slight rotations. So meaning that it doesn't have to have a larger degrees of rotation, but as long as there are some movements in it, probably small movements, then that can be analyzed as a pin connection. Okay, so for the roller support, then what if instead of these bolted plates you have something like a slot? Okay, so you have something like this. So instead of a circular hole, you're having a slot, then meaning that you allow some degrees or some amount of translation along this, let's say this is the x-axis, for example. Okay, so you allow some movements, and you also allow some rotation. So that's what we call a roller support. Okay, so The very obvious roller support is the wheel itself. So if there's a structure that has something like a wheel or something like this for, let's say, earthquake purposes or something. Okay, so that's an obvious roller, of course. Okay, so now we'll move on to the types of external load actions. So how do we model external load actions? External load actions. Okay, so the modeling is that we can model external loads as concentrated loads, line loads. Okay, that's number one. Number two is line loads. Then number three is the surface loads. Okay, so concentrated loads, example, or if you illustrate it, it's like this. So actually the point of action is the point of action is very small, that the area here is negligible. So we can just say it's a concentrated loads. So for line loads, we have something like this. By the way, I'm trying to draw here in isometric view or in 3D view. So meaning that this is X, Y, and Z. Okay, surface loads, we have, of course, from the name itself, we have a surface distribution of the loads. Okay, so for concentrated loads, our unit is, for example, in metric units, we have kilonewtons, or in imperial units, probably in kips. Okay, kilo in yes, I think that's kilo in pounds. For this, since this is a line loads, then the unit would be kilonewton per length, kilonewton per meter, and for this one, kilonewton per square meter. Okay, so where do we find these concentrated loads? So concentrated loads can be found in, for example, a girder. So the reaction of the beams of the girders okay, so let's say we have let's start first with the yeah, I think we'll draw a complete structural system. Say we have beams and then a girder and then a column. Okay, so one last thing, the slabs. So we'll include slabs here. Okay, so let's say this is slab. Okay, so the loadings would be, for example, the loads from the occupants. It is analyzed or idealized as a force distribution, surface load. Okay, so that surface load is then transferred into the beam. So the beam, or let's say this loads from the slabs, and then or plus the beam weight, then can be transposed as line loads. Okay, so let's say this is it. So it will be converted or transposed to line loads. So because you have these line loads, then of course if you analyze this beam, you'll get a support reaction, right? So you have support reaction here. So these support reactions will be a point load to the girder. Okay, so it's not that it's absolute, because probably what if the spacing of the beam is narrow, so probably you can we'll try to check if that's going to be a line load distribution. Okay, and then of course if this is a girder, if you analyze this, then you'll get a support reaction from from the I mean from the columns, then the support reaction will be the concentrated loads for to the columns. Okay, so another example for this surface distribution is the wind loads of the building. Okay, so in the next video we'll talk about structural responses, and then determinacy and overview of the structure, overview of the analysis of the structures, the different methods, and then we'll we'll do we'll go to the software now after that. Okay, so see you in the next video.